Hello everyone and welcome. In this tutorial, I'm going to define some particular important sets in mathematics. So first of all, I'll start with the set of natural numbers. Set of natural numbers, and it's denoted by set n. This set includes the counting numbers, and it starts with 1, 2, 3, 4, 5, and so on. So we follow with this pattern in which whenever I need a new number, all what I need to do is to add 1 to the previous number. Of course, this set is infinite set, never ends. It includes counting numbers because usually we use this set to count objects. The next set is the set of whole numbers. Set of whole numbers, and it's denoted by letter W. We can define this set as the union between natural numbers and the singleton 0. In which, if we look at the definition or at the set of whole numbers, instead of or in addition to the whole or the natural numbers, we have the number 0. So 0 is the only new element that we have it in the whole set. My next set is the set of integers, and it's denoted by letter Z. This set includes, or it can be defined as the whole numbers or the whole set union the whole numbers but multiplied by negative, which means that in addition to the whole numbers, we have the negative whole numbers, or basically we multiply every whole number by a negative number and we add it to the set. The next set is the set of rationals, and it's denoted by letter Q. So this set can be defined as x equal a over b, or its fraction, such that both a and b are integers and b is a non-zero integer. As an example, if I look at 2 over 3, 2 over 3 is a rational number because simply 2 is an integer, 3 is an integer, which means that 2 over 3 is a rational numbers, because as you see, if we compare with the definition of rational numbers, this number satisfies the condition or satisfies the definition. Another example, 0 is also a rational number because I can write 0 as 0 over any non-zero integer. For example, let's say negative 3. And at the same time, I know that 0 is an integer, and 3 here is also an integer, which means that 0 is a rational number. In general, I can also say that any number or any integer is also a rational number, because if I take a in z, then I can rewrite a as a over 1 in the form of a fraction. And at the same time, I know that a is an integer, 1 is also an integer. It follows that a is a rational number. But the fact is, not every fraction is a rational number. Why? Because if we look at pi over 2, pi over 2 is given as a fraction. But the thing is, pi is not in z, and this violates the definition of rational numbers. For this reason, I can't say here that pi, or in fact pi, is not a rational number. And based on this, I can define a new set now, and I will call it the opposite set, which is the set of irrational numbers. And simply this set includes the numbers that are not rational. That's why I can call it as Q prime, and it's the complement of set Q. Example, radical 2, radical 3, or cubic radical of 3, for example, pi, let's say the exponential, let's say for example logarithm, for example log 3, let's say ln, and other examples. All these numbers are not rational numbers and they belong to the set Q prime. Now I can combine all these numbers, or both sets, the set Q and the set Q prime, which is the set, all numbers that are rational and irrational in one set, and I will call this set to be the real set, the real numbers. That's why real set include all numbers, rational numbers and irrational numbers, and here I can say that every number is a real number. In addition to this, we can add the final set or the last set, which is the set of complex numbers. The set of complex number is defined as a plus ib, in which both a and b are real numbers, and I, the definition of I is equal to radical negative 1. Of course, this number does not exist or is not defined in the real set. That's why we call it the set of imaginary numbers or the complex set. As an example, if I look at pi plus, for example, radical 2i, this number is a complex number. Why? Because pi is a real number and radical 2 is also a real number. It follows that pi plus I radical 2 or radical 2i is a complex number. Similarly, I can tell, for example, the number 2i, this number is also a complex number. In fact, I can rewrite 2i as 0 plus 2i or i2, in which here I have 0 is a real number, 2 is a real number, it follows that 2i is a complex number. Also, I can tell that every real number is a complex number. And why this is true? Because if I take x to be a real number, one can rewrite x as x plus 0i, in which x is real and 0 is also a real number, and it follows that x is a complex number. Finally, we can draw a good relation or a relation between these sets, in which I can say that all natural numbers are whole numbers. And this is easy to figure it out because we already defined the whole set as the union between natural set and a 0. At the same time, I can say that all whole numbers are integers, because also from the definition of the set of integers, it's the whole numbers union negative multiplied by whole numbers. And I can also say that all integers are rational numbers, or the set of integers is a part of the rational set, because we already proved this, in which if we take any a in z, I can rewrite a as a over 1, and where a is in z by definition of a and 1 is in z, so it follows that a is a rational number. Also, rational numbers are real numbers, and this is from the definition of real set, in which is the union between a q and a q prime. And finally, all real numbers are complex numbers, because we said that if x is a real number, I can rewrite x as x plus 0i, where x is in real set by definition, 0 is a real number, so x is a complex number.